Good day, everyone. Today we are looking at geometric random variables. Now, you'll recall from the last lesson where we looked at binomial random variables. Binomial random variables are where we're looking at the number of successes in a given number of trials. And today we are looking at the number of trials that it takes to achieve one success. So how long it takes to get to the first successful trial. Geometric random variable, which we'll call y. It counts the number of trials to the first success. So with binomial random variables, we looked at the binomial setting, and then we were looking at the bins. So with geometric settings, we aren't looking at a set number, we are counting the number of trials. So we're going to change bins to bits. So the only thing that changes in the letters is the n, and that's also the only thing that changes in what we're evaluating. So B stands for binary. Binary. And once again, we have only two possible outcomes. And of course, one is what we call the success, and the other is failure. So you either have what you're looking for or you don't have what you're looking for. I is that each trial must once again be independent. Each trial must be independent. T, remember T is instead of S. This is what we can call our goal count. So the number of trials until the first success. Number of trials. S is that the probability of success is the same for each trial. Probability of success is same for each trial. Okay. So once again, bins and bits, the only difference is whether you are looking for a fixed number of trials or whether you are counting the number of trials. All right, let's look at an example. So for instance, we'll look back, we had an example where we said how many times did I get roll a 1 when I roll a six-sided die, and that was a bin. The success is that we are rolling a 1. The failure is any other number. Each trial was independent. We were counting the number of trials, so I might have said that I was going to do 10 rolls of the die, and I wanted to know how many times I got a 1. The probability of success was the same for each of them. Now in this case, we're going to roll the die and try to get a 1, but we are going to count how many times we have to roll the die before we get a 1. So the question here is, how many times do I have to roll a die before rolling a 1? Okay, so y in this case is the number of rolls to my first 1, and it's a 6-sided die. So let's look at the probability that y equals 3. So in other words, what is the probability that it would take me 3 rolls to get to get a 1? So in this case, what we are talking about is that it would take, so first of all, probability of getting a 1 would be 1 out of 6. So if it's going to take me exactly 3 rolls before I get a 1, the first roll will be 5 out of 6. The second roll will also be 5 out of 6, but the third roll will be 1 out of 6 because that's the roll that I actually get a 1 on. When we add this up, we get 25 over 216, which is approximately 11%. So if we generalize this, the probability that y is equal to a given value of k, in other words, that I will have k, it will take me k trials to get 1 success, will be equal to 1 minus p, where p, little p, is the probability of success. So the probability that y equals p is 1 minus p to the k minus 1 times p to the 1. So in our example, k was 3, and I had to do 1 minus p, in other words, 1 minus 1/6. I had to multiply 2 of those in with 1 of the probability of success. So k minus 1 is how many unsuccessful rolls I will have before I get my 1 successful roll. And that's our formula. Okay. We can look at what our expected value is, and what I'm going to be asking you to do is to read some pages in your book. So I'll put that at the bottom. You're going to read pages, you can do this after finishing this video, pages 399 and 400, and in that you will see a histogram, and what it shows is that, of course, you might keep rolling for a very long time, and you will keep going, and we get a curve kind of like that will keep going and get smaller and smaller, approaching 0, but it could go on indefinitely, or it will go on to infinity. So we're not going to prove we're not going to derive our mean, but suffice to say that the mean, or the expected value of a geometric random variable is, so the expected value of y, or the mean of y, will be equal to 1 over p. Okay, so we've now looked at the case where P of y equals K. You, of course, can also do the probability of y being less than or equal to K. And in that case, it would be the probability of y equals K plus the probability, not K, 1, plus the probability of y equals 2, and so on all the way to the probability of y equaling K. And we could use, to solve this on the calculators, the geometric PDF, and this would be the geometric CDF rather. This one would be the geometric PDF. So in class we can go over how to use that, or you can look in your textbook. I believe that's on page 400 as well. If you wanted to know the probability of y being greater than a certain value, what you would have to think about then is that means that it is basically the probability that y is not equal to 1 and the probability that y is not equal to 2 and the probability that y is not equal to 3, etc. Okay, all the way to the probability of y being not equal to K. Or in this case, it's greater than, so then this would also include K here. So you, in your assigned questions for this, I'm giving you just 3 of them. You'll have a question that's similar to that. So I've given you a little bit of a hint there. Page 405, numbers 95, 97, and 99. Okay, and that is the end of Chapter 6 material. So I'll see you in class. Have a good day.